I'm going to introduce Daniel. We worked together a few years ago, and when I joined the Space City board and we were discussing, what kind of people do we want to have come out here and talk, we talked about, iconic architects, but also we try to have architects come and speak who haven't really produced a whole lot of work yet. Daniel is kind of early in his career, even though he's been doing it for a decade or more. When I met him, we were both at SLM, and I got to sit next to him, and I noticed that he was doing some interesting stuff. He was working on Moon Village, which I thought was kind of ridiculous, but also kind of amazing that he could pursue such a thing in a professional architecture setting. So when he asked me if I wanted to help, I was like, of course I do. This is the coolest thing I've ever seen. And something about Daniel that really strikes me is that he has really unbridled optimism that things are going to happen. And he pursues his work with that mindset. There's no doubt in Daniel's mind that eventually there's going to be some architecture on the moon. And he proceeds with that kind of confidence to pursue his ends. And that, to me, is really encouraging, because a lot of times as architects or technicians, we find the limits of things. And it's really easy to say you can't do something. But being able to imagine something that seems impossible and work towards that is a pretty significant mindset to have. So as Daniel is working now as a professor, he's on his own, he has his own practice. I think it's excellent to have people who have that kind of vision, that they can accept that they're working towards something without knowing that it's possible. So I'm excited to have Daniel here, and I'm going to let him pitch his work. He's worked with a lot of different companies, but now he's on his own at Daniel Inocente Architecture, and I'm excited to see what his career turns into. And without further ado, Daniel, the floor is yours.
So yeah, as Jesse said, we're working at SOM together in New York, and as you guys know, New York breeds a different kind of architect. There's a lot of competition out there, a lot of great work. There's definitely no lack of ambition in that part of the US or the world, for that matter. And there's a lot of opportunity as well in terms of collaboration and opportunities to work on projects. So my background started at SciArc. I studied architecture at SciArc in LA. I was born and raised in LA. I got a chance to work at Frank Gehry's office straight out of school, which was very, I would say, lucky. Somebody from his office attended one of my reviews and said, why don't you come down, see what you can contribute to our firm. So right off the bat, I started working on the Guggenheim, and then I got pulled into other projects. I even got to work on his own personal residence, and that was actually quite interesting, just to see, how a star architect works together with his team and getting to engage very closely through that creative process. Along the way, I started getting more and more interested in science and technology. I really like the idea that architecture kind of pushes engineering to the boundaries, and when an architect says, this is what I want to do, can we make it happen? Then you go and you find experts in other fields to help you make that reality. And so I ended up working at NASA for a year. I got exposed to some really interesting engineering, and I just immersed myself in it. And after learning about science and technology and engineering and robotics and the way that we're pursuing space exploration, I thought, this is an awesome opportunity to think about the role that architecture can play in the context of space exploration, really in the context of humanity's future. And so I kind of made it a goal of mine to find that synergy throughout my career. And I've been working to make that happen, and I've been getting closer and closer as the years have evolved. Then right after working at JPL, I went back to work for Frank Gehry. I'm just giving you guys an overview, but I went back to work for Frank Gehry. Then I got to work at SOM eventually. I landed on the East Coast, working in the office of SOM for 6 years. And I got to work on everything from high-rise projects to transportation to mixed-use developments, and even space architecture, which I think is what Jesse was talking about. Was I took the initiative to build a partnership with the European Space Agency, and that really took off. It was kind of interesting, just the way that they embraced working with architects, working with engineers, structural engineers, and within SOM we had a team. I was leading that team and helping formulate the problem of master planning and developing space architecture, trying to define what space architecture really was and how we can have an impact. You know, architects, we're not engineers, we're not scientists. We have a specific skill set, which is almost like that of integrators. You know, we bring together a lot of different languages, a lot of different mindsets, and we try to bring a vision to something. This image that you see here, this is a photo taken by William Anders on the Apollo 8 mission. That was the first crewed mission that circumnavigated the moon. And what was really poetic about this image, you know, this goes back, I remember being a kid and seeing this image and thinking, like, who took that photo? How did we even get this picture? It's such a beautiful photo because it reminds us, you know, where we are, our place in the solar system, our place in the universe. And, you know, if you dig deeper into what space exploration has given us, it's really a gift of I would say depth and understanding and just the vastness of what's out there. And so that really puts things in context. And so as, you know, the kind of Apollo evolved, there was a lot of, I would say, like optimism for what space exploration could become. And you had scientists at Princeton coming up with all these visions, working with artists, working with architects, engineers. Everybody wanted to be a part of this movement. And these are images that depict this idea of like a O'Neill cylinder. Gerard O'Neill was a very famous scientist and slash engineer, and he started putting these kinds of ideas together, pretty much like transplanting Earth-based architecture into space and just making it visually provocative. But what was really cool about this movement, I'm sure at that time, was that everybody wanted to be a part of it. And just like today, you know, there's actually a pretty significant shift. If you guys follow some of the news that's happening with transportation, space transportation most recently with SpaceX, you know, this is really starting to ignite, I think, our imagination on what may be possible in the future. But going back to this, you know, this is an image that really inspired a lot of creativity at that time. And so when I was working on this ESA Moon Village project, we were developing concurrently with a lot of engineers throughout Europe, with the director general at that time from the European Space Agency, trying to define what a master plan approach would be on the moon. And this is something that, you know, it's not a small feat. And so you kind of have to approach it from the large scale, the macro scale, and the micro scale. And it was very important to think holistically about what are we designing? We're designing habitation systems, we're designing infrastructure. And as soon as you start thinking about habitation, you have to bring just a wide range of expertise to the table. Everything from power systems to thermal systems to looking at how life support systems work. And so it's a really tough challenge. And if you immerse yourself in this challenge, you really start to become aware of a lot of unique technologies that exist in the field of space that can be applied, you know, terrestrially. And so this really like opened up, I think, a lot of opportunities for us. So now kind of getting into it, what is space architecture? Well, space architecture has been defined by NASA very rigorously. Since NASA has a lot of history in, you know, doing a lot of research and science on the human body, but also on systems, there's already a pretty well-defined manual for what space or habitable spaces could look like and feel like in space vehicles. And that includes things like environment. So when you talk about the environment, you're talking about the internal atmosphere. How do you maintain that atmosphere? How do you control the carbon dioxide? How do you scrub the carbon that humans produce? Humans produce a lot of, you know, carbon dioxide, and if you just like if you're in space and you're breathing, you can choke yourself. And so having those systems in place which can move air at a very specific pace, at a very specific volume, and then having the ability to scrub that is an important technology that you see in space architecture. Water conservation is a very important aspect of this. The body consumes a certain amount of water, and so you have to think carefully about how much water you're intaking, how much water you're using for hygiene, how much water you're using for food production or for for basically like preparing your food. Contamination is another key one. There's a lot of protocol around contamination because in space, you have to think, if you bring something with you, some kind of a sickness or a virus, you're stuck up there with that. So you have to be very careful on what you bring with you. And then obviously there's a lot of other factors that play a role beyond that. In terms of habitability, the architect comes in and says, okay, well, what are the systems that we have to integrate into this habitable space? Obviously, you need exercise. You need to maintain your physiology while you're up there. You need medical equipment. You need to be able to provide stowage, a lot of stowage for consumables and also for crew use. And so there's a lot of things, layers of information that are pretty similar almost to like an architect's manual, I would say. And here's just like, the list goes on and on. I guess that's the point of this, but it's really important that as I started to like dig deeper into the human system drivers, I started to understand better the different relationships between each one of these systems and how they relate to other more abstract notions of things like, what is well-being or what is the human experience and what makes for a more productive space. So those kinds of relationships really, helped define some of the work that we were doing throughout this project. Additionally, there's a lot of crew interfaces, something that we take for granted because crew interfaces, they're not just there to control the vehicle, but they're there for you to be able to monitor and manage basically a machine that's keeping you alive in space. And so if you as an architect can come in and say, I'd like to design this interface, or position it in such a way where you can do multiple tasks concurrently or make space multi-purpose, you actually have a role to play in that. It's like you're not just given a product and say, here's a dashboard, put it there. You can start to define some of those parameters and you can even start to design the interface itself. And so that's the way that we thought about it. We thought about it holistically, everything from designing the structure, the space habitat structure, to thinking about the internal systems and how they work together. In space architecture, there's kind of three classes, if you will. There's the pre-integrated class, which is what you see on the International Space Station. The International Space Station, I won't go into too much detail, but it's really like just a big endeavor, a lot of different nations contributing different components to be able to build this large piece of infrastructure in space, everything from power to crew mobility to habitation spaces. Like the list goes on and on. And what makes that amazing is that when you have international partners working together to build something of this scale, you kind of get the best, of everyone, because certain nations are really good at certain things for some reason. The Europeans are really good at like life support systems, where transportation systems might be something that the US has actually advanced significantly. And then there's also modular systems like inflatable technologies, which were tested quite rigorously during the Transat project, which was a NASA-led project. And that project really tried to take this idea of fabrics. So what is an inflatable? In the technical terms, they call it soft goods technology. And really what it is, it's like a multi-layer system that starts with almost like woven, if you imagine like belts and woven threads. And then the weaving is kind of the core technology. A lot of patents have been created around this. And also materials have been invented to make this even better. And there's currently a lot of testing happening in the commercial sector as well. There's these things called private-public partnerships where NASA puts out some solicitation and then a company takes that on and says, I'd like to push this technology forward. And actually architects get involved as well because we're trying to figure out how do we take this technology and how do we outfit it, because it poses its own challenges. You have basically like an inflatable system that is compact, and then once it gets deployed, you have to figure out how do I make use of that added volume. And so that's an architectural problem. It's something that architects can solve. Now, in the context of the Moon Village, we were really just exploring ideas, but one of the ideas that emerged was this concept of an exoskeleton that would be a hybrid between a hard shell and a soft shell. And this emerged kind of from some of the work that we were doing in the practice of architecture. We're designing structures that had these exoskeletons and trying to figure out, how do we use the structure and express that structure and make use of it where best possible. So in this case, we took that advantage of the fact that a rigid shell could take on penetrations much better than the soft shell. And so what we did was we did this. We created an exoskeleton that would then terminate at bulkheads, and the bulkheads would have the adapters, and it would also have the windows, and it would have all the chases. And of course, this is at a conceptual level, we were defining this architecturally, but at a later phase with ESO, we started doing what they call the CDF, concurrent design facility study. So the architects design the idea, and then we pass it off to their engineers, and then we work through the problems holistically together. And that was kind of the idea. And at the same time, when you're talking about space architecture, you have to think about logistics. It's almost like a construction site, if you're designing a building, but you also have to define the kind of like the sequence of steps that take place to get your building done. Like the concrete comes first, the foundations, and then you pour this, put the steel, so on and so forth. So in this case, you have to factor in transportation, and you have to factor in the mass and the volume that a transportation system can actually deliver to low Earth orbit or to TLI, which is translunar injection. And so as soon as you start thinking about that, then all of a sudden new problems emerge. And those problems are, you need other systems. You need something like a tug. So a tug is almost like a bus, and that bus takes your payload, in this case a habitat, from LEO to TLI, through TLI to the lunar orbit. And so these are additional pieces of infrastructure, that's what we call them, infrastructure, that are needed to be able to take a habitat from Earth all the way to another celestial body or the moon, and then land it safely. Once you're in lunar orbit, you're orbiting the moon, and you're attached to this tug that took you there, had just enough fuel to get you there. Then you need to rendezvous with a lander, and that lander weighs just as much, if not more, than the habitat, because it has a lot of fuel and it's waiting for you there. So then once you attach and rendezvous with that lander, then you take it down. And once you're on the surface, if you can even get it that far, then all of a sudden you have to offload it from the lander onto a vehicle that is designed and engineered to be able to lift a habitat of this scale. And then you have to take it down to the final destination. So that's kind of what you're seeing here in these slides. It's the sequence of steps that it takes to get a habitat from Earth all the way to its final destination. But there is a lot of complexity involved. And here we're just trying to illustrate it as simply as possible. And now as you get deeper into the habitable structure itself, some of the problems we were trying to solve is, what is the duration? What is the mission duration? In this case, it was kind of self-imposed. We've seen on the ISS that people have stayed for up to a year or more, and you have a certain amount of volume for every given person. And in this case, we said, what if we pushed ourselves to maximize the payload capacity of a starship or a heavy lift vehicle, and then create a space that could last for up to 500 days. And that's pretty much pushing the boundaries of what's even possible today. But just, for the project itself, we said, okay, let's make that happen. Pressurized volume, we ended up with 700 cubic meters. Net habitable volume, after you eliminate all of the structures, all of the eclipse, all of the equipment, basically all the systems that take up space, we're left with a net habitable volume, and that's what gets divided per crew member for that given duration. And so, it starts to get really small really fast, because the longer your mission duration, the more material you need to bring with you, the more water, the more systems. And so that starts to eat away at the usable volume. But you need space. You need space for humans to be able to thrive, for people to do exercise, to have daily activities. And there's a lot of activities that take place. They're doing scientific work. They're doing research. They may even be doing some actual industrial work or research that needs to happen for us to make this sustainable. Here's a cross-section looking at this design. One key element was the airlock. It's a smaller component, but it's an incredibly important component, because without the airlock, you can't get inside. The airlock allows you to segregate the inside habitat atmosphere from the exterior. So it's basically like a vestibule. You go into the airlock, that airlock is sealed, and then once you close the door, you take off your suit, and maybe you're covered in dust, but that dust has been known to cause a lot of harmful effects on the human body, and it even damages equipment. And so you need to be able to doff your suit off, and then store your suit so that you can replenish the eclipse on the suit, because the suit itself is like a life support. It's basically like a mini habitat that wraps your body. And when you go out into the lunar environment, that thing is keeping you alive. So you need to be able to replenish it and repair it. It's the only way for you to escape if something goes wrong. And so the airlock attaches to the habitat. You walk into the habitat, and you're in the workstation. So this is kind of like the workshop. This is where you can get a little bit dirty. You have some of the control systems for doing EVAs, or what they call extravehicular activities. And then we designed this vertically, and so the only way to move vertically is to have a lift or to have stairs. And so we decided to do a combination of the two, because in some cases you may want to take things that you can't carry up, and in some cases you may just want to be able to move your own body up, and especially on 16G, it's much easier than on Earth gravity. Here are the floor plans, and you can see here that once the habitat is deployed, we ended up with 3 lobes, and there's these tunnels which connect to the airlocks or potentially to vehicles, and then you have all of the racks arrayed around the perimeter. One thing to keep in mind is that envelope, the exterior thickness, is realistically pretty thick. We're talking about maybe 200 millimeters or more, just to be able to accommodate all of the multiple layers that are involved in making that possible. And then on the right, you see the second floor. And then the third floor, this is where we had the crew quarters. And then on the fourth floor, we decided to put some kind of food production system that would advance the ECLIS, or the life support system. Because food production in this case, it's more than just producing food, it's also using things like biological systems to be able to scrub the CO2. So there's a lot of interesting technologies in that field. We can talk about that later. And then here are some drawings just to show the way that the geometry would work. And this is something that we wanted to think about carefully, because as architects, we also want to make this constructible. And so we started figuring out how much of the geometry can we inform based on our knowledge of the construction limitations of fabric. And then here are some details of what that section looks like at the window. So if you look at the top part of that section, that's actually the exterior. And then if you look at the bottom part of that section, that's the interior. And then there you see the mechanical chase, which follows the structure. And you can see kind of like the multi-layer system coming into that column. And then the window with 2 panes. The windows are really thick. You have to make them thick. Plus you need shutters on the outside in case there's some kind of micrometeoroid. So it takes a lot of protection. Here you see some diagrams of how we imagine that column and the fabric to come together. And you see there's different kinds of weaves you can take advantage of depending on the loads. So if you have cross-sectional loads, you can look at something like an ideal weave. That's what it's called, but it's more like a consistently spread out weave. And then when you have longitudinal areas, you can put something like an equatorial weave, which basically puts more material in one direction than the other. Here are some structural analysis diagrams. What we did here was we were trying to simulate how the habitat would deploy, and we used actually building structural software to do this. And with the team, we were trying to figure out what is the most optimal geometry given the pinpoints and given the interfaces. And we were getting pretty close to the form, but obviously, this is a very complex system to solve, so you would have to really solve the problem by building it. That's one of the key challenges here. And here's a diagram showing how the system comes together. What you see on the left is a wireframe of the structure, deployable systems throughout. You have a fixed floor, which allows you to integrate some of the mechanical systems, and then you have these deployable arms, which support the floor once you've deployed it and once you've installed everything that goes in there. What you don't see is all the racks that would be mounted on top of the fixed floor. And so that's something that would have to be considered. And obviously, all this has to be tied down, fixed, and it has to be prepared for launch. There's a lot of complicated things that we didn't get to solve, but it's still a lot of work that we put together for this project. And so the thesis of this, as I started from the beginning, was we wanted to figure out how do you start with an element like a habitat and then expand to make this more of a master plan. And so the idea was, if we design a modular system and then we take that same approach to a lot of the different elements, we can start to reconfigure a master plan that would evolve over time, over many years, with multiple partners contributing throughout the world, and the ability to even test some advanced 3D printing technologies in the future. And here you see this development happening, which is the Moon Village right at the edge of a crater. And the reason the craters are so important is because there's vast resources in the depths of the crater where no sunlight has hit, from the beginning of the formation of the solar system. And because of that, you have these water ice deposits. And water is critical because you can use it for life support, you can use it for fuel, and you can use it for other purposes as well, like radiation protection.
More than 50 years have passed since humans last traveled to the moon, and there's still much we don't know about the brightest object in our night sky. What would it mean to return to the moon today? To leave more than flags and footsteps? To create a sustainable home? It would open new avenues for science. It could kickstart an outer space economy. And it would allow us to create a new kind of community, to discover how we might live together beyond the Earth. The European Space Agency's concept for a moon village is an international endeavor, bringing together governments, industry, and perhaps private entrepreneurs to support a permanent human presence on the moon. If an earlier era of space exploration was driven by competition, this one will be defined by collaboration. What would it take to truly thrive in space? How can we make the moon feel like home? Built from a rigid composite frame and an inflatable structural shell, the habitat maximizes usable space and creates a sense of openness on 4 levels. The first phase of development will allow crews to live, work, and continue building the settlement. Gradually, additional infrastructure and equipment will arrive, and new habitation units can serve functions such as food production and science operations. Eventually, the Moon Village will grow into a thriving community, a hub for science, exploration, and even tourism. Visible from everywhere on Earth, the moon has always given humans something to aspire to, a place to set our sights on. And soon, it will be a place we might call home.
So this was part of an exhibition at the Venice Biennale. This happened just a couple of years ago, so it was really awesome to see that happen there. And one thing that continues to change, and I was just reminded of this just looking at this video, but it's kind of the priorities of NASA and really of the international community when it comes to space. I just came back from DC. It was an event where we had all these policymakers coming together, some engineers. I was the only architect there, I believe. And so my talk kind of took them off guard, but I got a really positive vibe from them. But what you see is priorities changing based on, obviously, politics. And what we're going to see in the next few years is we're going to see a lot of transformation happening in the aerospace world because of that change. And it's exciting, and it's also a big opportunity to see, what we can do at an accelerated pace. This next project I'm going to share with you guys was a follow-up. After doing this research project with the European Space Agency, I was contacted by some scientists at the University of Manchester. They're actually material scientists, and they wanted to figure out, hey, is there anything we can do with a material that we're really well known for? So I don't know if you guys know, but the University of Manchester, they're known for graphene. And graphene is supposed to be called the wonder material or miracle material. Applications haven't really been explored fully yet, and so there's a lot of opportunity for that material and technology. And by working with these scientists, we said, what if we take this idea of an advanced material using carbon fiber and graphene and push it to its limits? And so I came up with this concept of an observation station that could really take advantage of that technology. This is what you see here. I'm going to try and keep this one short because I want to go through a lot of projects. But what you see here is you see a lot of penetrations, a lot of windows. And so like openings and penetrations in the space application are a big no-no because you're obviously you're making the structure fragile and you're making it extremely expensive and very hard to build. But when it comes to working with fabrics like carbon fiber, actually you can do this pretty easily. And we wanted to test it. We wanted to see how can we build something like this. And so we actually went through the process of creating the graphene mix, building up the fabric, and we used a combination of different technologies. We wanted to use first 3D woven carbon fiber. We wanted to use a resin with graphene, and then we wanted to use a mold that was 3-dimensional that would allow us to thicken the structure where necessary. Basically, wherever you have a crease or any space in between the windows, we would have a thicker area that would take on the loads and transfer them more evenly. And some of the research we were doing at this time was going back to the Orion capsule when they were trying to figure out, can we build this out of carbon fiber? And there was some work done. What you see here is, this is a project that NASA supported looking into carbon fiber. And it's kind of cool. Like when you start to peel it away, it's really, what's inside is you have a honeycomb structure. So it's a metal. And then you have these thin layers of carbon fiber that are just like hand laid. It's a very manual process. And then you have these splicing elements, which you see like right there at the bottom. There's this delineated splicing element, and that brings together two pieces, the top half and the bottom half. And you basically have a cone and a barrel section. And then the bottom of it had these really cool lobes. And you can kind of see the guy standing in there. There's these structural beams spanning. And the whole thing is carbon fiber and titanium, or there's other metals in there too. But it's pretty it's just awesome to see that you can build this, make a lighter structure, and still work with the number of penetrations that you want to. So we took that. Here's some images of us just testing the material. You can see that there's a 3D woven fabric. There's a rib in the middle. And then we put that into a resin mix and we pressed it. And then the product on the bottom, you can see that's it's the size of, a book. It's not too big. But then we took that sample and we started just testing it, doing some analysis, testing to see how it would behave. And that was just a process, no funding, just trying to figure out what can we do with this. But from the architectural side, we really explored this design to the fullest extent. We took that idea here, you see that same section. So even though the focus was on the material technology, we wanted to explore architecturally what would that look like on the inside. And of course, you have to start from the hardest part, which is building the structure. And so you can see on the outside, you have the multi-layer insulation, and then you have the Whipple shield. The Whipple shield is what takes on the impact, and then it's broken up into different segments so you can actually bolt it on to the main structure. And then you have the window frames, and the window frames are also multi-layer. You have an outer pane for protection in case you have an impact, and then you have obviously the two inner panes. And on the inside, we also have a shell that covers the carbon fiber so that you can put chases directly inside. And those chases allow you to basically move electrical and fluids within the habitat because you need to be able to move, these systems throughout. This is what it looks and feels like on the inside. So we really wanted to just explore this idea of an observatory in space. What would it mean to design and build a structure like this and put it up in low Earth orbit and have it as a destination for people to go up there, look out, look back. It's both scientific, but it can also be a touristic destination. So, that's some of the space architecture work. There was a lot of projects happening in the space world. Like Jesse said, I was working on space work, and then I was also working on high rises. And what I'm going to show you is some of my work, my most recent work. I've been exploring ideas for high-rise buildings based on a lot of the work that I did when I was working on real high-rise buildings that are either built or in the process of being built. And one of the things that came up again and again was this idea of sustainability and structural integration, and how do we maximally make use of a building's surface area? Because if you think about it, the envelope of a building, if you walk in this building, you look outside and you see that there's a big envelope, there's a lot of opportunity for a building's envelope to do something productive. Architecture can be more productive. And so in a lot of my work, I try to explore how can architecture become more productive and produce something of value that can be used to operate the building. This is the East Rivers Tower project. When we started working on this with my team, we took a site, the biggest undeveloped site in New York, and we said, what if we build a number of high rises with one landmark tower that would incorporate solar panels on the outside, what you call BIPV, or building integrated photovoltaics. You can see here, it's on the East River, adjacent to the United Nations building. That's the UN building on the right. I think it was designed by Le Corbusier and Walter Gropius, among other architects. And then you see the Chrysler Tower, which is just like iconic. It's one of the most beautiful buildings in New York, and will be that for a long time. And then you can see on the bottom all of the key ideas behind this design. It's sustainability, there's ecology happening on the inside, systems integration, high performance exterior, biophilic design, and of course, we're building this for humans, and so it has to be human-centric. There has to be, ways of interacting with the building and the spaces that allow humans to feel like they're living in their natural environment. Here are some key diagrams just to show the articulation of the form. When you design a tower, you typically start with a form, and especially when you start to get on the higher, taller buildings, the form makes a big difference because of wind. And so wind exerts a lot of pressure on the building, and you want to be able to, what they say, confuse the wind cross-sectionally as you're going up, so you can mitigate the wind forces and not allow for natural frequency to take place. And so we did that with this tower, and then we introduced this idea of an atrium that would be blocked off a certain level, so it would be stacked and separated throughout the building, and that atrium would become almost like nature flowing through the tower. And then the last key move that we made was we serrated the glass. There's a lot of precedent for doing the serrated geometry. There's even some buildings that have done that with BIPV, but usually like in a vertical section. In this case, and I had also worked on the building in overseas in Asia, which is being built, where we actually did something similar, but in the cross section. And so this building is unique because it's on the East River. You have exposure to sunlight, and you can actually take advantage of that sunlight and use it for something productive. This is just to showcase the process. So my process when I design buildings, I use a lot of computational design. I use Grasshopper, and it's really just a tool. It's like the paintbrush for an architect. If you can use Grasshopper, you can flex a lot of different ideas, and you can very quickly visualize and quantify the impact that a design decision is making on your project, especially at this scale, because there's a lot of repetition, so you can do parametric and computational design pretty effectively. And I usually like to break up the systems. Design geometry is it's a very important part of design. The geometry then has to translate into structural systems, and so you need to be able to extract things like wireframes and points and vertices or vectors, because when you take that information, you can then hand that over to an engineer. I don't know how many of you have worked with engineers, but they typically take, they're not just going to take your Rhino model and do analysis on it. They want very specific information. Wireframes are usually the best. And then for the purpose of designing the facade system, you need to be able to subdivide and separate different facade systems. Sometimes you have spandrels, sometimes you have glass, sometimes you have fins. And so all these systems, of course, need to be separated and treated differently because you're going to detail them differently. And floor plans. We need to be able to maximize the usable area. You're designing, at the same time, you're designing the vertical transportation as you're designing the building. And so you need to look at the cross-section, the floor plan, and see how much area do I have that's usable, and is it optimal for the use that I want it to be? In this case, it's a multi-use project, so it's like office, housing. There's a lot of different purposes throughout the tower. Environmental analysis is also a key part of this. Nowadays, I mean, I used to use Grasshopper all the time, but nowadays there's amazing tools out there. So there's no excuse for any architect not to be using these tools. In this case, Climate Studio, you can basically take your design, put it into Climate Studio, and just do a quick solar analysis to look at the impact of shading on your building. But to push it a little bit further, you can do analysis on irradiation and then quantify how much energy potential your building is receiving throughout the year. And that energy potential, if you say, go and pick a product like a BIPV, you can then take that, put it on your building and say, hey, I could power, in this case, 600 homes a year. That's the equivalent of 6 million kilowatt hours. That's a pretty awesome contribution if you do it properly. And if you detail the facade properly, you can actually update it over the years. So if the building's going to be there for 100 years, every 20 years, you could say, hey, I have a new and latest and greatest technology for solar panel efficiency from 25% to, 40%. And yeah, that's the idea. There's actually solar panels in the space industry, which are a little bit more expensive, but much higher efficiency. And so imagine a future where we can take some of that technology and bring it to the building sector and really just like power our buildings more passively. So that would be pretty cool. And then here's us trying to figure out, okay, well, what's the ratio of glazing to spandrel to BIPV? And so we wanted to really try to balance these two. And you can see that there's about 46% glazing and 54% solar BIPV, and that's happening often in the in between areas where you have not visible glass, but where you have the floor stack, and that's a very important surface area that you can make use of. And then in the spiral areas, you can see that there's these gardens kind of weaving through the tower. And here's a diagram of a structure. It's basically a diagrid, and it's a diagrid with varying column sizes, and then the columns would just wrap the entire structure and span back to the core, and then that core would serve as kind of the spine of the building. And you see all the floor plates here. And here are some details looking at how the spandrel would work. It's all planar, it's all panelized, all planar. And we did some analysis on how this would perform, and the numbers kept coming back consistently. So it was really interesting to see that solar BIPV could actually have a big impact on that. But not only that, you can also use solar BIPV that is fritted, that isn't completely opaque, but actually allows the transmission of light. And so having light available, having natural light come in, but also collecting some of that energy, I think is a really powerful idea. And we could be doing that a lot more in our buildings. And then here's a cross-section just to show how basically like the infrastructure works. There's a lot of different buildings. You have housing, you have office, you have workspaces, you have entertainment. It's really like a city within the city. And you see that this is a trend in New York where mega projects are happening like Hudson Yards. And so the idea of creating a livable, viable community that is highly sustainable and hopefully self-sustaining could be really like the future that we're looking for when it comes to urbanism. And that was the idea behind this project. And by the way, there is a project actually going up on this site. So I encourage you guys to see what that looks like. And here's a layout of all the floor plans. And again, when you think about computational design, it's a very effective tool because you can very quickly produce and analyze what's happening within your design. And this is what I call the cookie cutter sheet. And I applied this technique to a lot of different projects. It's a really powerful tool when you use it right. You can even use it to lay out your building. In this case, you're seeing just a snapshot of some of the floors. You have the lobby, which is pretty much like the most vital level, because as you come in, that's where you decide, are you going to the hotel, are you going to the office tower? And there's a lot of different programs vertically stacked. And so circulation has to be organized and coordinated very carefully. And then on the right, you see an office floor. And you can see that there's a lot of open room. There's office spaces, there's conference rooms, there's common spaces, and there's that atrium where you can put a really nice garden and open space, collaborative spaces if you want. And here's another level looking at the Sky Terrace. and that's where you have the park. So it's almost like a miniature park within the tower. Imagine having a destination within your workspace where you can go and you can take some rest, or meet up with friends, and then maybe even work from that space without having to leave the building. But you can always leave a building. And then there's a hotel component. And so this works, actually, when you think about the building as it tapers, the bottom sections, which have the largest area, those work really well for office areas. But then when you get to the upper areas, that's where you can start to integrate hotels, because you have a smaller footprint. And hotels typically want to be a little more compact. And so in terms of, I think, just bringing a new idea to the table, it's how can you integrate all of these different ideas when it comes to sustainability, to energy, to building systems, to the way that you treat urbanism, and then trying to rethink the formula for designing a tower. This is another project. This was part of a competition that my team worked on. It was a very compact site. It's on Broadway, and currently there's no building there. They demolished the building that was there. And the idea was, what can we do on the site that's this compact, and also in the entertainment district, or they call it the theater district, and start to come up with a new multifaceted, multi-programmed tower that would include restaurants, sky gardens, residential, hotel, and even some co-working spaces. And so what we did was, we first started with the base. We wanted the base to be a very public, very open program. And the base leads up to a large terrace. And then from there, you see the tower stack. And the tower stack is very carefully organized. We have 1, 2, 3 terraces when you get to above the base or above the podium. And then you have a large interior sky deck at the very top. And here you see some of the analysis that we were doing. As we were designing the building, we iterated on the form. Again, applying the same processes, similar tools, looking at more carefully at carbon, especially carbon, like what is the production of carbon for the design decisions that we were making. And you can see on the right, there's a lot of different strategies. There's the idea of using electrochromic glass, using, I don't know if you guys have heard of VIP insulation, vacuum insulated panels. And because it's a curtain wall, you can actually carefully install the VIP, which is about 1 inch thick and provides a high level of insulation, and then just sandwich it with a metal panel. And that allows you to insulate the building really well, because it's a vacuum, basically. It's a really, really awesome technology if you can use it carefully. And throughout the tower, we were thinking about all these different ideas, including BIPV again, because we wanted to make use of, especially the upper part of the building, for collecting energy. And so one thing that you see here is that this is actually a double skin system. And what we have is two layers. So a double skin system where you have a ventilated cavity between the outer skin and the inner skin. And then through louvers, you can control the intake of wind. So if you wanted natural air to flow in during the summers, you basically open the louvers, air comes in and starts to condition the building. And if you wanted to heat that in the winter, you can close the louvers and then heat that cavity. And here you see the different materials that we selected for the project. Looking at copper, it's a really beautiful material. Some towers are starting to use that in New York, and they look awesome. Steel, you can't get away from steel. BIPV, electrochromic glass, VIP insulation, and other natural materials. And you can see the detail on the right. And here's a cross section. And here in this image on the right, you can see the louvers. So that's that cavity stack. And that's what allows wind to move through the building. And then the intake on the left. In terms of program, again, this was mostly residential. So you can see the apartments here. We were trying to maximally fit multiple units. We worked on including things like single bedroom, 2 bedroom, 3 bedroom. It varied. There's a different demand in this city, and so you have to think carefully about all the different mixes. This is the lobby entrance. It's a very compact entrance, but given the site circumstances, this is what we can do. And this is the podium level, and this is the crown. So these are just a few more recent projects that I just showed you guys, and this is me trying to, crack the puzzle of how can I have an impact on high-rise buildings, and I'm searching for that opportunity where I can find a path to applying some of these projects, some of these ideas to projects. And then going back to space, so while I was working on space ventures, there was an interesting collaboration that took place with a company called Lockheed Martin. We collaborated with a couple of their engineers on looking at designing a habitat that would be mostly human-centric. And so this is where we said, okay, what if we take this idea of a small, minimally viable module? Here you see a different configuration of multiple modules coming together. But what if we just focus on the interior outfitting and the multiple functions that can happen within? And so to that extent, we took a very close look at, what's out there. So the ISS is always a precedent, but the ISS is, it's microgravity, so it doesn't directly translate to a lunar surface habitat, but there is some organizational strategies. And one of the things that we try to avoid is having all these surface areas covered and cluttered with systems and gears. And then on the right, you see a mock-up of the Gateway, which is meant to be a destination for lunar orbit in the future. And you can see that there's a difference in thinking. There's a lot of change happening. There's some ideas about how to organize functions better and how to compact the space better. And so the approach that we took was, why don't we study the form first, study the envelope of the habitat, and we understand what we want in terms of form factor, and then work our way inward and then back to the form factor. And so here you see a few studies where we're basically like generating many options. For this purpose, we use what's called MMOD. I don't know if you guys, sorry, not MMOD, MU, multi-objective optimization. And so multi-objective optimization, it's a process that allows you to basically set parameters that you can optimize for, and then you start to generate a lot of different options. And so this allowed us to come up with many options. You see on the right just 3. And then those options were characterized in terms of the geometry complexity, in terms of volume, in terms of surface area, and the orientation of some of the penetrations. And going back to designing for the human, one of the key components here is radiation. And so radiation is a really important hazard to consider when you're designing a space habitat. And because of that, we wanted to take extra care to look at the envelope and see what can we put into the envelope that would allow us to increase the protection for the astronauts. And here you see a diagram. These are NASA dose limits. So based on different mission profiles and different ages, you have different limitations for what they call millisieverts, how much of a radiation dose you can get. But when you're on the moon, these are different. They vary drastically. But you see there's 2 different dose limits, one ESA and then one NASA. They have different ways of rating this. But we wanted to start thinking carefully about what are the materials that could help us and what are the strategies that we can apply. And so to that extent, we started looking at, again, the envelope. In this case, we have the MMOD on the outside, we have the thermal layers, the thermal insulation, and then we have the structure. And for the structure, again, we thought, what if we could use carbon fiber? And within the carbon fiber, we would have, mechanical chases. And in addition to that, we would also have a water jacket. But the water, you don't see it here because the water jacket would be locally placed where the crew quarters are, where the astronauts are going to spend many hours resting. So the environmental design played a big role in this. We wanted to try and simulate circadian lighting. Circadian lighting for us meant, especially in space, meant finding ways to simulate the sunrise and the sunset, but in a confined environment where you're on a different celestial body. And the challenge there was, what are the key technologies? Well, LED lighting is a big one, looking at different surface lighting techniques, whether you have lighting overhead, lighting in your personal spaces, lighting in the floors. And here you see the design that we started to come up with. There's multi-lighting, multitask lighting happening throughout. And then what you don't see yet is all of the furniture is actually tucked away. It's tucked away in the floors. The furniture comes from the floors. And even the stair you see in the back end, that's extremely compact because we started designing the stair to be almost like a shifted stair, and that would allow you to reduce the amount of area that the stair would take up. On the left there, these 2 units that you see here, those are the hygiene stations, and then you have some working equipment and science equipment, and of course you have this table that actually moves up and down. And then on the second floor here, we have the crew quarters. The crew quarters we wanted to make multifunctional. And for that purpose, what we ended up designing was a retractable wall that would slide out and provide you with more volume. So every individual would have additional private volume, and they could even, close themselves off if they wanted to sleep. And so that the idea was to try and really bring the space to life using some very basic strategies, and at the same time, using integrated LED technologies and displays to help control the environmental lighting. And here you see another, looking back, this is back on the first floor. And I'm going to show you guys a video that kind of captures the overall design essence. All right, so back to Earth. So this is actually a project that I'm building in upstate New York right now. I called it the Atom, and it's a really cool project. So about a year and a half ago, I purchased a piece of land, and I wanted to say, okay, well, how can I test a lot of these ideas of using, integrated technologies, smart home systems, modularity, sustainability, and so on and so forth. And so we purchased this piece of land. It's about 1.6 acres. It's overlooking a lake. And here what you see is together with a partner of mine, we designed this building, which is 6,000 square feet. It's really just we were trying to test a lot of different things, but almost the entire house is modular, with the exception of the basement. It's being built in Pennsylvania, and then the modules, they come in different elements. There's boxes, there's panels, and then there's some structural elements that are basic, like steel LVL beams and columns. And what we wanted to do was actually create a passive house. So it's passive house certified that would produce more energy than it consumes on an annual basis. And to get to that, we had to design the envelope very carefully. What you see a large window. So a lot of people might think, well, that's not actually very efficient. And because we wanted to minimize the amount of windows that we have on the main body of the building, we put this large window, and we also wanted to orient it towards the view. And because we wanted to make this passive house certified, we had to go with passive house windows. So all the windows you see here are passive house certified. And so the way it's going to be built, which is really cool because we've been working through this very carefully, is they're going to be taking the units up a hill. They're going to be sitting them on top of the fixed foundation. And first, the units in the back get installed first. So you're looking at it right now from the entrance of the site. And then you have the wing, which actually has the master bedroom and the garage. And then those units get installed afterwards. And then the front of the house is all panelized, where you have the double or triple height space that's actually 30 feet tall, that atrium. That's all panelized. It's panelized with panels that are 8 feet by 20 foot tall. And the roof is also panelized. And those all get installed on site. Our goal is really to try and install this house in like a week. And with modular construction, you can do that pretty effectively. The fabrication process for a house like this actually can take no more than a month if you do things right and if you do things really expeditiously. But what does take time is the site work, especially for a site like this with this complexity. And here's the floor plan. It's a very basic floor plan. What's key is the technology that we're putting into the house. We're putting a smart home system that monitors everything, like the power, the temperature, the PPMs, even having some circadian lighting. We have fabric ceilings in some areas where the fabric is backlit, and you can sit down, and if you have a cloudy day, you can simulate the sun, and hopefully it makes you feel better. But the power system is really cool because there's smart switches in the power wall, and then with those smart switches, you can monitor everything from your phone. So the house is actually able to use, and we're using a software for this, but it's able to monitor the consumption from your lighting, from your mechanical system, from your appliances, and then it can optimize the use of that and switch back and forth between the grid and the battery to minimize your cost. But because we're producing more energy than we need, it's actually kind of cool because then we can use that energy and power an EV. So we have a battery that we can use in the garage that we're going to be using to power an EV car. But the goal of this is really, it's an experiment, and we want to just repeat this idea. And it's a really cool project and process that I've been exploring for the past year and a half. And hopefully it'll be done by spring of next year. And here's some pictures of the house, or some renderings of the house. This is looking at the large double height space. Earlier this year, there was a competition. I don't know if you guys saw the 3D printing competition. And we wanted to try and explore some ideas about how we can use, again, geometry and a lot of the different things I've been talking about. But 3D printing, it's a very interesting technology. And when applied right, you can do some really cool things with it. One of the key challenges with 3D printing is basically the printable volume. It's like when you take a desktop printer, you can only print within a certain volume. But when you're thinking about it on the scale of a house, you have to be careful about how you first place the printer and then how much volume you can print. And the height limits you for how much 3D print you can do, but then you can actually install, doesn't keep you from building something on top of it. And because of that, what we wanted to do is we wanted to create a prefabricated roof system that would come with basically like everything from skylights to even solar panels, and then build that in a factory, thinking about some of the work that we were doing on the Atom, and then install that on the 3D printed wall, potentially once the 3D print is installed. And so here you see a diagram of the layout. It's using a hexagonal structure. The inner partitions are all built on site because it doesn't make sense to 3D print some partitions. But the envelope is all 3D printed at once, including the window openings and the door openings. And you can see that there's like a subtle shift to the geometry. And this was helping us understand if the geometry is helping us reinforce the structure. And in fact, it does provide a lot of reinforcement. It introduces a little bit of complexity, but that tilt gives you some additional structural stiffness. And then here you see a cross section. And you can see on the right a diagram showing how the prefabricated roof would come together. Basic wood framing with rigid insulation, and a metal roof and solar panels on top. And so what we did was we tried to look at how many configurations can you come up with. If we're building a community, you're limited by the volume, the printable volume, but you can take this idea of the hexagon and start playing with it in multiple configurations. And you see that diagram on the right. You can have certain clusters that are either studios, and then you have a 2-bedroom, or you have two bedrooms, or you have just one large continuous, built-up print, which could be broken up in different ways. And then here's a depiction of the construction process. You start with, the foundation. You have to build a foundation for the machine to be able to roll back and forth. So that has to be pretty solid. And you put that on tracks, and then you have the walls coming up, and then you have the roof being installed in 2 pieces per roof. Here's some pictures looking at it from the bottom and from the inside. It's really hard to fit. Actually, for this competition, it was really hard to fit the inside. It was actually a real challenge, trying to get as much as possible. So I don't know if I told this to you guys, but I'm also a professor at ASU, and I've been teaching architecture there now for a year and a half. And more recently, I've been appointed professor of practice of space architecture. And so one of the things that I wanted to pursue as I was teaching a studio was this idea of building a new center for ASU where you could explore science and space. And so I actually had my students do a similar project. We picked a site very close to the campus, and I wanted to try and solve that problem myself. But it was the idea of building a facility where you can experiment with large-scale space exploration technologies, construction, habitation, a lot of things that are really interesting in that part of the world. Because right now, I don't know if you guys know this, but ASU just launched a new program in space architecture, and I am a professor of that program now. It's going to be starting next year, and I can tell you more about that. I'll actually share a link if you guys want to pursue it or look into it. But it's the second in the country, and I believe it's going to be the third in the world. And it has the potential to become a really amazing program. So this project, it's a really big building, and we were exploring this idea of creating a large ecosystem within the building envelope. And because it's mostly labs and a lot of office spaces and working spaces and some even high bays, it really wants to be like a bar building. So the idea was, it started with the bar building. We started kind of creating these iterations of how the bar could maybe wrap around itself. And what you see here is like a roof looking down where you have two courtyards. You have one open air courtyard and you have one large greenhouse. And here's the site plan. And so the idea was, can we put this on a site not too far from ASU and make it like a destination? It's not just a building, it's a park space. It's both exterior, interior park space, and it has an abundance of energy collection to power all of the needs of the building. And here you see the program broken up. It's about 1.4 million square feet. The bottom of the building is mostly the robotic construction and exploration facilities. And then that spills out to the surrounding areas, as well as the astronaut and analog and training facilities. And so the astronaut analog training facilities, we would have everything from hangars to conference rooms to offices, even having some outdoor exploration areas where the students could do and perform some work. And then here you see a floor plan, and this is what I was talking about when I was explaining the bar building configuration. You see the multiple spaces kind of wrapping around this large inner green space. Here's the second floor, third floor, and these are some elevations. And again, we were doing analysis, a lot of analysis on the roof, looking at how much solar gain we can get, how much power we would provide, trying to figure out, what are the best strategies to make this a sustainable building. And these kinds of mega projects, they're not uncommon. You guys have seen them in some of the large headquarters. And so I think, building like this could be a really powerful tool for creating new innovations, especially when it comes to space exploration and having that dialogue with all of the different engineering departments, especially at a campus like ASU. And here's just some images of what that main space atrium would look like on the inside. And we even included a museum so you can display some of the work being done. And here's a flyover. And I think Jesse's flagging me for time, so we're going to end it after this. I didn't get to describe the process of designing the building itself, but it started with a lot of computational design, parametric design, looking at the form factor, orientation, and of course, part of that also was analyzing the floor plan, because you want to have certain lab spaces be a certain depth, and lab spaces have both wet rooms and dry rooms where you perform certain kinds of work. And then where you have the high bays, you need really large spaces like 60-foot tall ceilings to be able to bring large pieces of equipment in. And so the building form kind of reacts to that program as it wraps around. And you can see here, this is where you get closer to the high bay areas. And yeah, thank you.
you.